Welcome to Society of Amateur Radio Astronomers, Radio Astronomy, Constant Variables and Formulas. Lesson 9. We'll go over the Pulsar Observation Analysis, determine the period, p dot, dispersion measure, electron density, distance, and age of selected pulsars. This is an example of a Presto output, which is one of the primary software packages to detect pulsars. This is an example of the brightest pulsar in northern hemisphere, B0329 plus 54. The 0329 is the approximate right ascension. The plus 54 is the declination, which is the phase versus time chart. You can see a good pulsar will have a good signal all the way up. This shows two signals side by side. Very thin signal is a good detection, which means a high signal to noise, and the noise floor is down here. Also across the frequency chart, this is the frequency you were observing it at, should see a good amount of data or signal across the frequency band. Dispersion measure should peak at the dispersion measure expected, which this does. The data we're going to look at today was collected here. For this pulsar, the period is approximately 0.714 seconds. P dot, which is actually the spin down rate, how fast the period goes down, because the pulsar actually starts spinning down over time. P dot is the derivative of the period, which tells you how fast the pulsar is spinning down. Now, dispersion measure is in parsecs per centimeter cubed. A parsec is a measure of distance, approximately 3 light years. And the purpose of the dispersion measure is that frequencies don't arrive at Earth from the pulsar at the same time. And the dispersion measure actually allows you to calculate that. Primary source of pulsar data is the Australia Telescope National Facility. There's the website below. If you go to that website, you get the option to select various parameters in the pulsar database. And when you hit table, it'll come up with the view on the right. And at that point, you can look up what the right ascension declination is, what the expected period is, P dot, DM, the ages, and various other parameters that you want to look up. It also has a very nice feature that it gives you the reference for where the data came from. So you're just not assuming that it's right. You actually have a couple references in there. Let's look at some calculations. On the left is the data for B0329 plus 54 from the ATNF database. On the right, we're going to use that data to calculate other information. Distance can be calculated using dispersion measure. The assumption is that you know the electron density of the column of space between you and the pulsar, how many electrons per centimeter cubed. The average is 0.03 per centimeter cubed in the galaxy based on some reference sources. So we'll start with that. So you take your distance equals the dispersion measure, which is the 26.7641 parsecs per centimeter cubed. Divide that by 0.03 per centimeter cubed, And that gives you a distance of 892 parsecs. Now we're going to put dm in front of this because there are other ways to measure pulsars like parallax and various other things. And we'll show you, we'll use that as an alternate distance if in the database. Next, we're going to determine what a better electron density is. Because as you can see, the ATNF database, the alternate distance is 1695 parsecs, which is almost twice the distance of what we just calculated using our average electron density. So we're going to go ahead and use the dispersion measure and the alternate distance to determine what electron density we would need in order to get the 1695 parsecs. And if you look down here, you'll see that the number comes out with 0.0158 per centimeter cubed for electron density. That is how many electrons per centimeter cubed it would take to equal the dispersion measure at that distance across the galaxy. Next, we'll go on to age. The age of a pulsar is equal to the period divided by 2 times the p dot. So let's take a look at what that answer is. If you take the 0.714 seconds period, divide that by 2 times the 2.048 times 10 to the minus 15th seconds per second is what the p dot units are. Come up with a very large numbers of seconds. The conversion from that large number of seconds to 1 year is 1 year is equal to 31,536,000 seconds. So the age, if you divide the big number by that conversion factor, is 5.532 times 10 to the 6th years. So now you successfully determined distance, electron density, and age of a pulsar using data from the database. Now let's go back and look at some actual data that amateurs have collected. That these are Presto charts from Deep Space Exploration Society. They regularly do pulsars, and it's www.dses.science. This is a chart, Presto chart. So you see they got 2 good peaks there. This is B0950 plus 8. So if you zoom into this area here, you end up with the period that they measured of 0.253 seconds. And the dispersion measure came out to 2.982 parsecs per centimeter cubed. One thing to note on the Presto, when you collect this thing, P dot does not come out very well. So in your analysis, you need to go grab the P dot from the ATNF database and not have it from, not use the Presto output. Okay, when you do that, your distance and dispersion measure ends up using the 0.03 per centimeter cubed average would be equal to 99.4 parsecs for this pulsar from the Earth. Now, if we go and look at what's a better electron density estimate, we end up with 0.011 electrons per centimeter cubed. The age equals 17.464 times 10 to the 6 using that equation. If you look at the ATNF values for this, period 0.253065, the actual measurement came out very close to that. The dispersion measure 2.96927 parsecs per centimeter cubed. From the ATNF, we got 2.982 parsecs per centimeter cubed. That also came out very close. And note the alternative distance, which might have been done by parallax, is 281 parsecs. Okay, that is the number I used here. Our dispersion measure collected divided by 281 parsecs to get the better electron density. If you plug that number back in here, you will get the 281 parsecs. This tells me that the column of electrons between Earth and the pulsar is a lot less dense than the average. Let's go on example 2. This is B1133 plus 16. Look over on the Presto chart, you see two very good peaks. Good data coming across. You got a good number coming up here on the peak for the dispersion measure. The data collected, the period is 1.188 seconds, and the dispersion measure is 4.86 parsecs per centimeter cubed. And we're using the ATNF database for the P dot. The distance via dispersion measure using the average, you get 162 parsecs. If we use the alternate distance in the database, which is 372 parsecs, you end up with the better electron density estimate of 0.013 electrons per centimeter cubed. And the age comes out with 5.045 times 10 to the 6 years, which is extremely close to the age in the database. So it appears that the collection nails the period and the dispersion measure. It's not extremely good using the average to the 0.03 per centimeter cubed for all pulsars for the distance dispersion measure. So that's why you should compare it with the data in the ATNF database. What that does indicate is that the average, that the electrons per centimeter cubed in the column of space between Earth and the pulsar is less dense than the average. That's good information. And that this method using the collected data gets really close to allows you to get really close to the age value. If you like this video, like and subscribe. Join SARA to start your hobby of amateur radio astronomy. Go to our website, www.radio-astronomy.org. Thank you.